Maybe introduce yourselves too, because
I'm Chris Wilson, and
I'm Sam Owens.
we're PhD students under Maarten. We're going to talk you through a bit of work that he did with Dr. Tom Grylls, trying to look at numerical simulations of trees. Yes, thank you. So as we all know, trees are really important in the urban microclimate. They impart drag, they affect radiation, transpiration, and they have an impact on aerosols as well. So it's really important that when we're trying to model the urban microclimate, we think of ways to model them, but as has been said, they're really complicated. So I'll pass over to Sam and he'll tell you a bit about how we try to model them.
So what we use in our research group is an LES code called UDALAS, which is an atmospheric large-eddy simulation framework designed for urban environments. So it includes the capability to model the transport of pollutants by solving the conservation equations. So the way you model trees is essentially everywhere you have trees, and I'll talk a bit about that in a moment, you need to modify your sources and sinks of those governing equations. And that includes the governing equations of momentum and also temperature, humidity, and pollutant concentration. And the way we do that in UDALAS is, and someone's already touched on this in this session, is the fact that trees at LES resolution, so 1 to 10 meters, say, are kind of partially resolved. The way we'll deal with that is to kind of just treat them as a homogeneous. I don't know if you can hear me. I don't know am I good? Do I need to speak the mic? Treat them as a homogeneous substance that exists within each computational cell with a certain set of properties. Those are listed up there. The key way, the key thing to mention is the way radiation is treated. It's essentially treated as one-dimensional, with the radiation coming from above and the tree composed of a number of layers. And the way they can interact with the surface is through a kind of rudimentary surface energy balance, in which you can get shading on surfaces directly below trees. And they obviously interact. The surface energy balance of the tree is obviously affected by their properties in terms of the transpiration and the sensible and latent heat fluxes that go along with that. And this is implemented in UDALAS with a two-way coupling, so the air will feel the effect of the trees. So this is just some images to show a validation case of a single tree, actually, so kind of an infinite tree extending into the direction of the into the screen. So the results show that this so-called minimal tree model, which was designed to kind of capture the behavior of trees whilst not getting bogged down in too many parameters, it's 11 parameters, performs reasonably well in this case. And so now I'm going to pass back over to Chris, who will discuss this parameter space a little bit.
Yeah, so the minimal tree model, which is 11 parameters, and that's a lot of parameters. So what you can do is, if you try and reduce it down, you can actually achieve 4 dimensionless parameters that is a lot easier to handle. So you can see here that these are the 4 parameters that Maarten and Tom got to when they did their redimensioning of the problem. And they have the decoupling factor, which basically describes the importance of atmospheric factors versus the surface properties of the leaves. And then we have 4 fluxes effectively. So we've got a radiative term, a transpirative term, and then a ground heat flux. And what they thought was that when you look at the balance between the radiative and transpirative terms, you can actually find out some quite interesting things. So if we look at this graph that they produced, you've got the radiative term going up and the transpirative coming across. And then they have the net tree cooling coefficient. You can see lines of constant tree cooling coefficient. And also the tree cooling ratio, which is the dashed line. Now, the net tree cooling coefficient is basically a measurement of does the presence of this tree increase or decrease the atmospheric temperature? And then the tree cooling ratio is saying, is the cooling more caused by the radiative effect, so that's the shading, or by the transpiration? And this splits it up, you can see, into different spaces, and you can see that they see, you can have a net heating caused by trees or net cooling, and within that, the cooling can be transpirative or shading based. But you can also have this net reduction space, which is where the area is still heated, but the tree's presence reduces that heating rate. And really, the point of this tool, what they hope is that people can just look and see, if we're building an urban area or looking at the climate, where do the trees sit within this space, the trees that we're dealing with. So then they went and looked at a load of different studies that have been carried out, and they used all the parameters from those studies to see where the trees in those studies would sit within that diagram. And you can see that across those studies, they found that they had net cooling, net heating, and net reducing trees. And then to give a specific example from the work of Shasucha Bar et al., you can see that in that particular study, they had, in one case, they increased the leaf area index, which is the A equals 0 up to A equals 1.75. And within that, they were all in the cooling regime, but the mechanism of cooling, the amount of cooling, was varying as they went through. And then in another element, they changed the relative humidity, and actually by doing that, when you go to 100% relative humidity, that transpiration term drops, and they actually got into a heating regime. So this is just contextualizing the work they've done and showing how it fits in with some other things. And I'll pass back over to Sam to talk a bit about pollution.
Yeah, so with regards to air quality, I think, as it's already been mentioned in this session, trees have this kind of competing effect, which is that in an urban canyon, they can stop, they can inhibit exchange with the flow above, because they're just a physical barrier, which can, if you have pollution inside the canyon itself, it's trapped by the tree. But then they also take up pollutants using their leaves. So what this study was all about was essentially looking at different situations to see, what's the total effect of these two effects. So the simulation setup here is of a series of canyons. Again, infinitely in the y direction, and there's a tree on either side of the canyon. And this was simulated in both a neutral boundary layer and a convective boundary layer, because buoyancy effects clearly also can have a big impact on this exchange between the canopy, between the canyon and the boundary layer above. So if we look at the figure on the bottom left, we can see that this is for the neutral boundary layer. You can see that on the right, and this is showing the velocity profiles. You can see that the velocity is indeed much smaller when you have trees, showing that you have less exchange. And if we go to the top right, I think this is again the neutral case. The two different scenarios we're considering here are an emission-dominated regime, in which you have a source of pollution within the canyon itself, and on the right is a background-dominated regime, where you kind of have where your pollution was generated somewhere far away, and it's flowing over in a kind of uniform concentration. And you can see that at pedestrian level, so I'm still looking at the top, at pedestrian level, you can see that actually the effect of trees is pretty significant, and in fact it can cause air quality to deteriorate, and this is shown on the bar chart on the bottom right left. And this effect you see in the neutral case. You don't see it in the convective case, but you kind of get very close values, and I'll touch on that on the next slide. However, in the background-dominated regime, you don't see this. So trees always have a positive effect on air quality. They always improve air quality. So in order to look at this, so in these bar charts, which we can go into more detail later, but just to touch on it, they're showing both the pedestrian level concentration and the canyon average concentration. And you have different results for both when you consider both of those. So it depends what quantity you're interested in. If you are interested in the canyon averaged values, then you can kind of do a fairly simple kind of like single, some kind of averaged equation for what you expect the concentration to be within that canyon, based on various parameters and your background concentration, various other things. Again, the maths is in the paper, and I encourage you to look at that. So it's just a one-liner there. But what this shows, what the process is doing a Taylor expansion of the exchange velocity as a function of the leaf area index. And when you do that and arrive at this expression and consider the assumptions that you make in a background-dominated and an emission-dominated regime, you find that, in fact, in the background-dominated, you always get an improvement in air quality. Whereas in the emission-dominated one, you might not. So there's actually there's a constraint on the relationship between this delta UV, which is it's the gradient of the exchange velocity with respect to the leaf area index against the deposition velocity. So yeah, the upshot is that you end up with this limiting, you end up with a limiting case, and if you run the numbers on using the parameters that they used for the LES study, you'd find that in the neutral case, you'd expect the air quality to improve under the presence of trees and deteriorate in the convective case. That's actually not what they not found. They didn't find that in the LES study. But that's when I said, we look back here, it's actually very close in this case. So it's probably just due to the modeling assumptions made in the min-watering model. But yes, I think that's about it. And given that we've got 1 minute left, I will finish there.
Yeah, we'd like to thank Maarten for giving us the opportunity to sit on his behalf.
It's been great.
I was wondering what kind of chemistry you have in the model in terms of evolution.
There's no chemistry in this, but in our model, there you can do some basic chemical reactions like the null cycle and this kind of thing.
Right. So trees in your model aren't actually emitting any aerosols then.
No, not in these simulations.
Question right here.
Yeah, how do you treat differently in terms of NOx and PM?
Yeah, so I probably didn't explain that very well, but yeah. So that in this situation, the NOx is the localized emission, what's called emission dominated regime, and the PM 2.5 is the background one.
But they are treated equally in your model.
Well, in terms of their values, or in terms of their
how they are
physics.
solved.
Yeah, physics is the same. Yeah.
But the NOx is coming from vehicle emissions
Yeah.
in the canyon.
Exactly.
Is there some parameters that can be put into the model to change the diffusivity or based on the molecular properties of? You know slightly more about pollution than me. He hasn't modeled exactly the same passive scalar, has he? Or has he? Just for the line source versus the background. It must have done something slightly different. I think he did. They can set like the maths of the, they can make a change.
Okay, we'll just take one more. I saw one back there. Yeah.
Yeah, just a quick comment. You discovered two regimes. One is the background dominated, another is kind of the source located dominated. So you didn't give information about the intensity of the turbulent intensity of the approaching flow. Would that affect those two regimes you just discussed?
Yeah, I think so. Well, so they did consider the neutral and then the convective, which obviously has a massive difference on turbulence intensity. But in terms of two different neutral boundary layers with different. So the way we generated the flow in this case was using a precursor simulation, and I think either they applied some kind of surface roughness and did a flat plate thing, or they had some actual. But yeah.